let's get started then. Last class, we did some examples of determining the area between curves is sort of what it's called in textbooks. And we finished the class by sort of motivating the next logical step if we're going to think geometrically. And that is, if we can use integration as a means to discuss the size of a region in the plane, a sort of planar region, if you will, then our intuition suggests that integration might be a useful tool when discussing size in 3 dimensions. In the typical English word for talking the size of an object that is 3-dimensional, or is the word volume. So let's just remind you of an important definition we made. So last class, we motivated our next topic. By defining volume for what I'll call basic shapes, or I shouldn't say shapes, that's a bad choice of word. Basic solids. So I'm using the word basic here in a very, I guess, colloquial, basic English way. But just to remind you of these things, if I have some sort of, that's a very ugly straight line. But if I have, say, a brick or a box, I don't know what physical thing you want to envision, but I'm trying to draw this creature as best I can. So if this thing has a height, and it has a width, and it has a length, whatever you want to call it, then it's defining the size of this thing is just length times width times height. So we're all going to agree that that's how we're going to associate a numerical value to the size of that sort of region, or that object, if you will. Okay, so that was one shape that we agreed on, and then the other shape, and its sort of closely related cousin would be this sort of cylinder. Oops. So anything that looks like this, it has a height, and then we say that this is, circular top. So it has a radius. So the volume here, we all agree, is pi r squared times the height. So these are things that we're all going to agree to be true. We're making these definitions. And using these definitions, we're going to define the volume of more general regions. So let's make this clear. Using the above definitions, we can define the volume of more general solids. Does anybody have a question? Okay, so if we look at these two pictures suggest something. If I were to take this box, whatever you want to call it, and if I look at it, there's a couple ways you can visualize this. You can say I'm going to take my box and I'm going to look at it from one perspective, so that we often call this a projection. So, for example, if I take this cylinder or this can, it looks like a cylinder. You know, if you think about what it looks like from one perspective, it looks like it is a rectangle. And then if you look at it from the top down, you know, if you stand high above it and hold it and look down, then since its top is a circular shape, it looks like a circle. So in general, if we have any solid, we might imagine that if we look at the cross sections of the solid and we can understand the area of that cross section. I mean, look at this box. What's a cross section? Well, imagine I take a knife and slice it vertically. So if I take a red pen and if I cut this thing down and I make sure that my knife remains perpendicular to the base, I get this. So this is the cross section. And what is the cross section? The cross section is a rectangle of area. Well, what's its area? Its area is it has no, like, in the left or right direction, there's nothing, because it's living in the front and back direction. So what is its area? Its area is W times H. So we can think of this box as really being made up of infinitely many, say, slices of paper or rectangles. A good way to visualize that is, here I have a stack of paper. Right now, this stack of paper has a thickness. It has a width. It has a length. So we can compute the size of this paper. But we also note that we can imagine that this sort of rectangular box that I'm holding in my hands right now, if we can also imagine it being made up of lots and lots of sheets of paper. if I go to the next page and I look at this sort of this cylinder, instead of taking a vertical slice, what if I took a horizontal slice and sliced it perpendicular to the side or parallel to the base? Then I get this slice. So here the cross section has area pi r squared. So what I'm getting at is we're trying to think about an object as being made up by sort of, you know, any solid is really just, if you imagine infinitely many two-dimensional objects placed together to create a solid. So if we look at another picture, let's try to sort of draw a more arbitrary solid. What if I had a solid that looks like this, sort of? Whoops, that was bad. Maybe you can imagine that this is like a fancy piece of art. If once it, this is it's like my pen gets drunk at the end. Can't have that. Again, if you imagine this as a solid, so all the cross sections, if we cut it a certain way, look like circles. So the issue with this particular shape, which we didn't have on the previous page, is on the previous page, all the cross sections were circles of the same exact radius, where here, I am trying to draw the shape where that might not be the case. Another shape that might be a little easier for you to make sense of this is if I were to draw a cone. Here, all cross sections, if I take them horizontal, are also circles. Now, it doesn't necessarily have to be circles. We can draw other shapes. Before I do that, does anybody have a question? So, for example, maybe we'd like to know how a pyramid. So what does a pyramid look like? A pyramid has, say, a square base. And if you want, let's use a different color here to help really emphasize this. Let's use yellow. If I take any horizontal cross section, I have squares. or I could do rectangles, but let's just assume for example that this particular creature has a square. Maybe we call this X and X. So what do these pictures suggest? Well, they suggest the following analogy of what we've done in the past. So the above drawings suggest that if we have a formula for the area of cross sections, we can define volume as the following. Volume equals some integral from one point to the next of the area formula of the cross sections. So notice I'm using some careful words here. I say the above drawing suggest. I don't suspect that this is obvious to most people, and it's very rarely obvious to students in a Calculus 2 course that this integral just jumps out. But if I can remind you of our strategy that we've used a few times already when it comes to integration, we take whatever it is we want to analyze. Here it could be a pyramid, and we slice it up in a certain way. And by this picture, I'm taking my pyramid and I'm slicing it horizontally, and then I examine one of those horizontal pieces. And I notice that one of those horizontal pieces of my pyramid can be regarded as one of those blocks, at least approximated as a box. And then I can say, oh, I get it. If I approximate each slice with one of these boxes or one of these little cylinders I defined earlier on, then I get a Riemann sum for the approximated volume of my solid. But we learned back in Calculus 1 that if our function is continuous, if our area function, if this quote unquote A is continuous, which it clearly would be for a square or a rectangle, it clearly would be for a circular region, then we know that Riemann sum can converge to something when we take a limit. And in fact, we know what that limit is. That limit, by definition, is the integral. So to illustrate this, let's actually work out one of these. I don't know what the best one is to do, the easiest to learn. But if you go to Google, I'm going to share this with you. So let's go to Google. Hopefully you see this. And I say volume of a cone. And the first thing you see is that Google spits out the formula, pi r squared times h over 3. And so the question we have is, how does Google get this formula? How did someone derive this formula? How could you derive this formula? Similarly, if I said to Google volume of a pyramid, you'll see that Google spits out that it's the length times width times height divided by 3. And the question is, why? Why is that the volume of a pyramid? How could one deduce that formula? So let's do one of these to help, sort of teach you how this works. And hopefully you can then be brave enough to suffer through the pain of learning it yourself. That's what I always say. So let us go. So okay, now if we want to sort of invoke an integral, and if we want to not just bring an integral into play, but if we want to bring in, remember I said we need a function that describes the cross-sectional area. If we want to do that, what we have to do is we need coordinate systems. We need to set the problem up correctly. So the most important part with this is the setup, because without a proper setup, it's impossible to do anything. So let's draw our cone. But when we draw it, let's think about sort of the geometry of our cone and how we might come to figure out sort of what's happening. So I don't want to use too many letters, so I'd like to keep this thing as simple as possible. So I'm going to draw my cone like this. I'm going to draw it like it's sitting on its circular base. Boy, that was an ugly cone. Let's fix that. Let's try to at least. Let's draw a prettier cone. Let's try to get as pretty as possible. Use some lines. So let's imagine our cone has a specific height and its base has a specific radius. So just to sort of tidy things up, let's suppose the height is, say, 10. And let's suppose that the radius is, I don't know, say 5. So notice I'm saying the height of this creature is 10, not the length of this sort of, not the length of the side. I'm saying the height is 10. All right, so how do we get this set up properly? So there's lots of ways you can do this. We need to decide how we wish to attack this problem. So if I think about how I want to do that, I remind myself What do I want to take advantage of? Do I want to take horizontal cross sections? Well, that seems to be wise because they're all circles. Once we have a system, we need a formula for the area of the cross section. Now, we know the area of the bottom, the circular base, the area of the base is pi times 5 squared, but we don't know the area of any other guy. So one way to get a formula is to use some ideas from geometry. Like similar triangles. But another way is to use basic ideas about linear functions. And it might not be obvious what I mean by that right now, but what I'm going to do is I'm going to turn this creature on its side, and I'm going to put it on my coordinate system. So what I want to do now is I want to take an XY axis. And I want to turn this thing on its side. So how would I turn this creature on its side? Well, I turn this creature on its side, and I know that I have the following. If I turn it on its side, it looks like this. And if I have it sitting there, I can say a few things about these points. Now imagine that the x-axis is going right through the center of this cone. You know, you're going to have a little bit of an imagination here. So this is your x-axis. But we do know some points. We know that if we imagine that the x-axis goes right through the center of the cone, we know what this point is. And what is this point? Well, we know the height is 10. So the distance, this point is 10. And then we also know the y-coordinate because we've assumed that the radius is 5. So we have 10, 5. Thus, we can use basic algebra that we learned many moons ago to determine how steep this line is, or the slope of the line, and hence the equation of the line. So you can imagine that there is the line that goes along this blue side, and what is this? This is the line y equals what? Well, what's the slope? The slope is 2. Right? Excuse me, the slope is not 2. The slope is 1/2 because it's 5 over 10. And since it goes through 0, 0, this is nothing more than the line y equals 1/2 x. So now let's just pick any point we want on this x-axis. What is this corresponding area of this corresponding slice? Well, if this is the point x, what do we have? We have the area of x is pi times the radius squared. Well, the radius would be the exact point here, which is x comma 1/2 x. So literally, I put 1/2 x in here because that's the radius squared. And so we now have a perfectly good equation or perfectly good formula for the area of the cross section. Does anybody have a question or a comment? Okay, so then if that's the area of a given cross section, it seems reasonable that the volume is then the integral from 0 to 10 of a of x dx, which becomes 1/4 pi times the integral from 0 to 10 of x squared dx, which you can readily integrate as 1/4 pi, and then you integrate this, you get x cubed over 3 from 0 to 10, which of course simplifies to 1/4 pi times 1,000 over 3. Yay or nay? Does this match the formula we showed you on Google earlier? Are there any mistakes? Are there any logical gaps? So if you do some arithmetic, if you simplify that number, that's 1,000 over 4, which of course is 250. So if I go to simplify this, I get the volume is 250 over 3 times pi. Does that seem correct? Does that match our formula? And the answer is yes. Because another way of writing this is pi, and then the radius is 5 squared. The height is 10. over 3, which matches the formula we saw earlier on Google. So what you could do if you wanted, and this is a great exercise to actually learn things, is you can go and replace that 10 with the letter H, and you can replace that number 5 with R, and you can do the same calculation and you would derive the formula that you see on Google. Does anybody have a question about this? So what's interesting about this is that even though we didn't verify it in general, you could easily do it. It would not be difficult for you to verify this formula in general, and it also wouldn't be difficult for you to understand why this definition even makes sense. Again, why does this definition make sense? It makes sense because, and let me be very clear, when I say makes sense, what I mean is it's not just an intuitive definition, it's the technically sound one if we think about Riemann sums and approximating first. If I think I'm going to approximate this cone by slicing it up into 1,000 pieces, then all those thousands of pieces are little circular cylinders. And we define what the volume of those are. So if I have 1,000 of those, I can add up the volume of those 1,000 pieces and I get an approximate volume of the cone. And then if I do 10,000 pieces, I get another approximate value. And if I do 20,000, and what I'm seeing is a limit that happens if I do it for 20 or 30,000. And so what we can do then is it makes sense to naturally define that limit of those approximations, the limit of that Riemann sum. It's only natural to define that as the precise volume. So I really hope that you take the time to dig deep into that and try to understand what I'm saying there. I can't do that for you. That is the discovery process that only you can do for yourself. And if you take the time, and for most human beings, it takes quite some time to go through that, but it's a rewarding thing once you make sense of it on your own. You're like, oh, wow, interesting. I made sense of it. Does anybody have a comment, question? I get my caffeine in. Is anybody alive? Is anybody even there? I don't even know. I just assume you're all paying attention and taking copious notes. That's a big word, copious. That's a wealth test word. All right. Questions, comments? All right. So this example suggests an even more general phenomenon is happening. And what do I mean by that? Well, we were able to deduce this by thinking of the cone as sort of being stabbed by the x-axis. And so this also sort of suggests that there's other ways of envisioning many types of solids. And so we want to kind of use that right now to breeze into the more general case. So another way to imagine the cone is to start with a triangle and rotate it about the x-axis. Notice I'm using the word imagine. So let me sort of illustrate what I mean by that. So once again, I take my xy axis, and what I'm going to do now is I'm going to draw a triangle. So here's my triangle. Let's imagine we had the same scenarios before. This is the point 10, 5. And of course, we know that this line right here is y equals 1/2 x. And what I want you to do is imagine that I take this region and leave the bottom fixed and rotate this region about the x-axis. And so I want you to sort of imagine that what happens is this point 10, 5 will rotate around in a circular manner. Oh, that's bad. Maybe a little more careful with that. So maybe it'd be best to think of it like this. So what you need to imagine is you need to imagine that each point on this top line rotates around the x-axis. And so if the point's here, what happens? It rotates down and around to here and then back up through to the other side. If the point's here, it rotates down and around to the bottom and then back up through the other side. And then, of course, this point rotates down to the bottom and then up to the other side. So I'm imagining sort of this triangle rotating around and tracing out a cone in three-dimensional space. So if we do it in this manner, so under this construction, we call the cone a solid of revolution, because it can be generated, at least in your imagination, by rotating some plane region around a fixed line. So there's some good videos on the YouTube machine that are worth checking out. If you just go, for instance, I mean, heck, I guess we can give them free advertising. If I go to Google where did my page go? And I go to volume of revolution, and I go to videos, you'll see that there's the YouTube machine has lots of videos to help you understand this stuff. So I would encourage you to go look into visuals, to go online, because there's some really good animations that help you visualize what's happening that we just can't do on you know, when we're teaching on a whiteboard. You can even switch it up to solid of revolution, and you'll see, here's one of my favorite videos. It's very, it's a good way of showing you what's happening. You take a plane region, and you get this plane region by using one or two curves. So right now they're using some basic curves to generate a plane region, and then you can generate a solid by rotating. And then how do you analyze that solid? You chop it into pieces. Look at the size of the piece. And you approximate it using those shapes we discussed last weekend, earlier in the class. And that's how this works. No, I don't want to see ads. Anyhow. So does anybody have a question or a comment? Someone is chopping. All right, so Paul, you're asking a question. Okay, so here's a good question. So the question is, if we're puncturing the cone down the center, so it probably goes better back to this picture, why is the net area not 0? Well, remember, we're not calculating area. If you were trying to calculate you're getting a couple things a little confused. We're not calculating area of anything. We're calculating the volume of something by adding up areas of other pieces. Now, the areas of the pieces we're adding up can't be 0 because they're circular regions. So their area is going to be a number bigger than 0. What you're getting, I think you're getting mixed up is you're thinking of the following. So this is actually a good talking point, because this can easily be confusing. So don't confuse the area of a 2D region with the volume of a 3D region. So if we just draw a quick picture, if I have some curve and I look at the region that it forms with the x-axis. So let me just shade it in to be. So what you need to understand is here, the red area is equal to the integral from A to B. And I got to be very careful here. It would be net here because there's a piece under the x-axis. That would be f of x dx. If I'm talking about a volume like in the previous problems, so if I draw, I have to draw a more detailed picture here. If I have some curve and I rotate it, if this solid is generated by rotating something, so what we showed here is that this is different. If this is the curve y equals f of x, then the volume here, volume would be the integral from a to b of pi times the function squared, because this is the radius squared. Because remember, this point, any point right here would be x comma f of x. So these are two different things. And this is, this goes to, what this comes down to is, this is the kind of stuff that you don't really pick up on in class, and you don't pick it up sort of just doing like robotic homework problems where you just plug things into a formula. Where you really understand and distinguish between these two different types of problems is when you're trying to do this on your own. And what usually happens is you're not going to make sense of it at first. Most of us mortal human beings struggle trying to understand this. It's just very, very, I mean, I even myself, when I was learning this many years ago, I probably didn't really learn it until I started teaching it. I just probably didn't. I might have been able to solve problems and get many of them correct, but oftentimes, here's a challenge in calculus. And I've mentioned this to you, those of you who had me last semester. Understanding calculus is not the same thing as being able to solve problems using calculus. Many of you will just solve problems and figure out how to do it, but you might not really understand what it is you're doing. You're just sort of mimicking procedures. I mean, you can even use the metaphor of driving a car or flying an airplane. I mean, most of us don't know the first thing about how an engine works in a car or how suspension works, but we do know if we hit this button or put this key here and we push this and do this, we can drive. And with practice, we do it pretty well. But how the car works, many of us aren't quite sure. Just like most airplane pilots aren't aerospace engineers. So that's not to tell you not to worry about why it works, but it's to challenge you to, I don't want to use the word suffer, but sometimes it is. It is a process to learn and understand this stuff. And so if I go back to what you're seeing on the screen, on the left, we're talking about interpreting an integral as the net area of some region. Where on the right, we're asking you to interpret an integral, a different integral. A different integral. Now you can imagine, I could take that red region that's on the left and I can rotate that to get a solid. And if I use the correct formula, the formula on the right, I would get the volume of that solid. I mean, think about it. If I took this red region and I rotated it, I would get a solid. It'd be an interesting looking solid. Because what would it look like? Well, let's draw the picture again. If I took that red region, looks something like this, right? So if I rotate that about the x-axis, what I get is so this piece will rotate down here, and you're going to have the solid's going to look like this. It's going to have a pinch in it. It's going to be like a kink. So here, let's be very, very clear. Area, and in this case, it's net because there's a piece under the x-axis, is this. Here, the volume is a different integral. So this would be a great example to try to sort of gauge or be your barometer for how well do you understand what's happening here. And it's not easy, but it is something that with enough practice, and there's a lot of what I call false confidences too. And it's part of the learning process. There's so many times where you're sitting there in class or watching me on Zoom, and I do a problem or I say something and it clicks. You think, at least. And you say, oh, okay, it makes sense. But then 2 hours from now, if you try to do the same damn thing, you're completely lost. And then you feel like you failed, like you don't know what the heck's happening. And that happens with learning. There's lots of times where you feel like you finally get something, only the next day to figure out that you're lost again. But that happens to everybody. It happens to me. That's just part of learning. And so you got to use that as a challenge. And you got to use that as also a reminder to yourself that it's perfectly natural to be confused by this. It just is. If you look at calculus books and math books and physics books and, most science books to be specific, one thing you'll find in textbooks is lots and lots and lots of problems. And that's not to torture you. It's because anybody who's ever learned this stuff knows one thing, that the only way to learn it and learn it right and understand it is to do and do and do. You just got to do it, and you got to do more. Practice, practice, practice. So, I'm not going to force you to do it, but I can encourage you to. I don't know. Hopefully that answered your question a little bit, Paul, and hopefully you guys will think about it. And don't forget, it's really hard for me to try to draw. The picture on the left here is a two-dimensional object. The picture on the right is, we're supposed to imagine, is a three-dimensional object. Okay, any other questions about this example? So what we often give this sort of this a name. So the strategy, or I should say strategies, because you can think of it differently if you'd like. This is often called volumes or volume by slicing. And since the quote unquote slices are circular discs, so, hold on, we have chaos. Oh, we have a screaming kid. Hold on a second. Sorry about that. Teaching from home is, kids, they don't understand boundaries. Do whatever they want. All right, so anyhow, we usually give even more specific names, because if we look at what the slices are, they're you can think of them as discs or depending on the case, washers. We use those names as well. Boy, that is an ugly W. Someone should turn me in for poor penmanship. So if you're looking for things to Google for practice to help, things like the disc method, the washer method are sometimes used. You know, you guys know my philosophy. I think most of you do because you had me last semester. I am not about memorizing formulas. I think that's a waste of your space in your brain. What I am more concerned with, what I would encourage you as learners to do, is to understand why something's true, understand how something comes about. That way you don't have to memorize it, you just know. So it's memorization, you know. I mocked you guys, I think, last semester. I shouldn't do it. But I always find it interesting when like people are sitting there like reading flashcards. So if you use flashcards to study, that's great. But I just feel like it's just I don't understand it. It doesn't seem to be an effective or efficient way of learning. Now you might disagree. You might say that's how you learn. But for me, I really have a hard time memorizing things. And maybe that's because I don't like doing it. I feel like if you just do things over and over again, and you really strive to understand them, then what happens is they become second nature to you. You know, I use the same story all the time, but when you're driving and you see a traffic light, you don't have to slow down and pull the driver's manual out every time and say, oh boy, what do I do? You just know what to do. Just like if you're falling, if you trip on the steps, or, you know, usually we have instinctive ways of doing things to catch ourselves from falling. And that's the way I would encourage you to look at learning math and science in general, is trying not to memorize things, but to use things enough that they become second nature. Now, of course, the way often we teach school is the opposite of that. We make you take tests and we do that, but you guys know my philosophy on all that. So anyhow, let's do an example to see kind of what these standard problems look like. Before I do that, though, does anybody want to ask a question? Cool. Okay. All right. So let's do an example. So the region bounded by y equals x squared, y equals 0, and x equals 1 is rotated about the x-axis. What we want to do is we want to determine the volume of the resulting solid. Now, it's not necessary that you draw pictures, but I highly encourage it. I mean, you could solve these problems if you without drawing a picture, but I just think that you should always draw pictures. So if I go to the next page, I'm going to draw this nice and pretty. So what do we have here? So if this is 1 and over here is 1, what does the curve look like? Well, y equals x squared looks like this. Oh boy, not good. Sometimes it's, we're having technical difficulties with the technology. So that's my pour. I'm going to try one more time. Tell you what, drawing on this thing is not, it's like a skill all in of itself. So the region I'm after is this region, which I'll mark in red. So what happens if I take this region and I sort of rotate the red region about the x-axis, what I'm going to get is I'm going to get like this horn-like sort of shape. It's going to look like this. Ah! Oh, man. So here's my solid. It's sort of like a horn. Maybe some of you played an instrument. I don't know. So I get this horn-like creature, and I want to know the volume of it. And so the volume, and this is the main point of what we were trying to teach earlier, or at least motivate, is that the volume is the integral from A to B of these cross-sectional areas. But in this particular problem, we're going from 0 to 1, and the cross-sectional area is pi times the radius squared, which is the function in this case. Again, what I'm doing is I'm picking any point, you know, what's the cross-sectional area of this circle? Well, it's going to be depending on the radius, and the radius is given by the function. And so in this particular problem, that is f of x is what? F of x is x squared. So this just becomes, pi can come out front, and then this becomes x squared squared, so that's x to the 4th dx. And when you compute the integral, you get pi over 5 times 1, and the answer is pi over 5. Does anybody have a comment or a question? Questions, comments? No, that's it. All right, cool. Now, another scenario which we should think about is the following. So let's phrase this question slightly differently. The region bounded by y equals 2 roots of x and y equals x is rotated about the x-axis to obtain a solid. Determine its volume. So this is a standard way a problem like this is sort of constructed. Okay, so let's draw a picture of this. So you might need a little bit of reminder of what these curves look like. So let's draw the first one. The first one is the square root, but we're multiplying it by 2. So, and then the other one is y equals x. So y equals x. Looks like that. And then what's the square root function look like? Well, the square root function looks like this. So this is y equals 2 root x. And then, of course, the green is y equals x. And then the region that we are interested in, which I'll shade in blue, is this. So we're not finding the area of this region. What we're doing, and by the way, it's worth pointing out that it's not hard to deduce what this point is. It's 2, or what is this point? Where do they intersect? This is the point 4, 4. How do I know that? Because when I plug in 4 in both equations, that's what I get, 4. Now you could also solve that if you wanted to, but or you can just deduce it. So here's what happens when we make this happen. When we rotate it. That's a very weird looking creature I drew there. So let's put it over here so it's more clear. We're going to take this region and rotate it. And so what's going to happen when we do that? Well, you're going to get a bullet-like outer shape. And then in the inside, it's going to have sort of this cone hollowed out of it. So you need to think of this as this is sort of hollow. Again, you're going to have an imagination here. It's really difficult for me to draw this, but this guy is very similar to the YouTube video I showed you. And so the slices have, you know, a hole in them, so to speak. So, and it's really hard for me to sort of make this clear on this video, drawing here. I'm probably making it more messy. It's probably not as helpful as it could be. So here's what we have, though. If we go to the next page, and again, if you have a question, please stop me at any time, ask questions, whatever you want to do. If we go to the next slide, and this is one I really want you to concentrate on when you're trying to learn this. So look at the cross sections. So what do they look like? Well, the slices, if you slice them down, they are so this is a washer. It's hard for me to, you know, to draw that, but I encourage you to go back to that YouTube video. Again, if I go back to the YouTube machine, it can't hurt for me to do this again. And all I have to do is just do solid of revolution. and then click videos. It's usually one, there it is right here. So this is a perfect example of this. It's a very similar problem. We use 2 square roots of x. They're using square root of x. And then they use the line 1/10 of x. So their region's slightly different, but the idea is the same. And when you rotate, you get this hollowed out cone in the middle. So that's very much what our shape looks like. And when I say the slice is the cross section, you see there's a hole in the cross section. So we often call this in the English language a washer, or at least it resembles a washer. Okay, so if I go back to our whiteboard, that's what kind of we want you to think about. And so this means that the cross-sectional area is going to be a circle minus an inner circle. So what does that mean for us? Well, that means the following.
What? Still searching YouTube for math help?
Oh my God, YouTube's yelling at me. So here, AX is the outer area minus the inner area. So in this particular problem, that means it's going to be pi times, well, what was the outer radius? The outer radius, if you go back, is given by the square root function. And then the inner radius is given by y equals x. So that means the outer one would be, this is 2 root x squared, minus pi times the inner radius, which would be x squared. So of course you can clean this up. This is pi times 4x. So let's pull out the pi. So you're left with 4x minus x squared. So note our function is not just one piece in this scenario, it's actually 2. And this is a very important component of this problem. And again, I would encourage that you ponder it and make sure you truly understand why. But with that in mind, we can now finish the problem. The volume is the integral from 0 to 4 of pi times 4x minus x squared dx. So we can pull the pi out and we integrate. It's 4x squared over 2 minus x cubed over 3. And our bounds are 0 to 4. So when you plug in 0, everything's going to disappear. So you're left with pi, and then when you plug in 4, 16 times 2 is 32. And then when you plug in 4 here, you get 64 over 3. And then the last thing you have to do is you have to do your basic arithmetic, which you can multiply 32 by 3. When you multiply 32 by 3, what do you get? You get what? 96. All right. And then 96 minus 64. And then after your second grade math exercise, what you end up getting is what? 32/3, I think. And so the volume of this guy is 32/3 times pi. provided we didn't make any air. So I ask you to ponder that and think for a few seconds if you have any questions. If you think I maybe made an air. If you want to ask me what's going on in the upstairs of my house with my kids, I think they're killing one another. Does anybody have a comment, question? So here's a cool, fascinating thing about this. What you're starting to see is nearly every object. I always found this quite fascinating, at least the objects we've studied so far. Most solids, the volume of most solids that you encounter in your everyday life have pi in them. Pi is everywhere. It's really fascinating. Does anybody have a comment or a question? Okay. Comments, concerns? So, as I said earlier, the best way to learn this is to do it and then do it and then do it. And what you'll find, to be honest with many of these, is they're quite challenging. And you're going to make mistakes early and you're going to make mistakes often, and that's just part of it. Any questions? Going once, going twice. All right. So if there's no questions about that, I think it would be a good place for us to stop. And I'm going to post the next assignment. And I'm going to give you a supplement there's another way that you can envision volume if you sort of look at your solids from another perspective. And that's called the shell method. And so we'll give you some stuff to learn about that and some problems. And then we are going to, on Thursday, we can answer any questions you may have about any of these problems. Does anybody have a question? All right, if you guys don't have questions, I say we will reconvene Thursday. All right. Going once, going twice. All right, guys, take care. I will see you.